Welcome back. We're doing the Gaussian mixture model, EM for the Gaussian mixture model, and we're getting close. We're just about to get it. So we were down here computing the expected value of zik, and we checked back up with our model, and we found that the probability that zik equals 1 is alpha k. And zik, the kth coordinate of this vector zi, it's a Bernoulli random variable. It only takes values 0 and 1. And so the expected value of a Bernoulli random variable is just the probability that it's equal to 1. So that means the expected value of zik equals alpha k. So we can use that down here. So let's use that. This equals the sum over I of alpha k. And obviously this doesn't depend on I, and there's I, and I is going from 1 to n, so this is n times alpha k. Alright, fair enough. That was nice and easy. Now let's think about this side. So once again we have linearity of expectation. We can move this through, simplify things a little bit. Let me just put the given little x here rather than keeping on writing capital X equals little x. And zik, zi, the vector zi, is independent. By assumption, these draws are IID. So the ith z is independent of all the other of the x's other than xi. So this is equal to the conditional expectation given xi. And this is exactly the thing going back up. So let's go back to up to our model. This conditional expectation. This is the thing that we computed here. Because this indicator function is precisely equal to zk. Or if this was zi, this would be zik. It's 1, the indicator is 1 when this is true, and that's the same thing as the kth component. So this conditional expectation of zk or zik given x is equal to this thing. And this we can compute directly. We know x, or in this case it's going to be like xi if this was zik. We know what the x is, we know xi, and we know what all the parameters now are. These are not the theta, so back down here. This is the conditional expectation under theta 0. And we're assuming that we know theta 0. So that's the key, that's the first sort of key thing that's going to make this work. That makes life easier when we're doing EM, is that we're assuming that we know this theta 0. So that's a key point right there. Since we know theta 0 now, we can just compute this just, analytically. Because these are the parameters. This would be like, the theta 0k or whatever. Mu 0k, C0k. These are the parameters that belong to theta 0. All right, so I think hopefully that was clear. So we can just compute this. So this is just some number that's a function of all those theta 0 and all. And let's just call that number. Let's write it over here maybe. Let's call that number. So, well, I'll just put it in here. Let's call that number RIK. It depends on I because it depends on xi. This is actually a function of xi, and so this is, maybe I'll write RIK is a function of theta 0, xi, and k. But let's just abbreviate it by RIK. All right, so we can compute that. We get those numbers. And let's call this sum something. Let's call this n sub k, because it doesn't depend on I. All right, so now we've got we can solve this, right? We can solve this for part of theta, at least. We don't get all of theta yet, but we get part of theta. We get alpha k. Alpha k, remember, is part of theta. And so alpha k equals nk divided by n. And our first step is complete. Okay, so that was nice. Now let's do blue. The next sufficient statistic let's tackle is, let's do this one. This one looks relatively easier. This one's a matrix and this one's only a vector. So maybe this will be easier. So we have sum over I, zik, xi. So once again, we're going to have we're going to have this sort of expression that we need to solve for part of theta. Sum over I, zik, xi, given x equal to the expected value of, again, sum over I, zik, xi. And let's do this part first again. Actually, let's do this part first. I think this part's easier on this one. So linearity of expectation moves through. Xi is given. It's part of x. So that pops out. And we get the conditional expectation, zik given x times xi. And just like before, this is just depends on xi. And so this should be, that's a capital Z there. That's not clear. It's a random variable z. And this is just the same thing as before. This is what we defined as these RIKs. So this equals sum over I, RIK, xi. All right, nice and easy. Okay, now this one's a little bit more complicated because we're taking the expectation over both x and z. But it's not too bad. We can do it. So we'll move the expectation through, and we can use the law of iterated expectations, sometimes they call it. The expected value equals the expected value of the conditional expectation. Zik, xi. That should be, that should be a capital X in there. It's random X. Random X, not the given X. Xi given, and now let's make it given. I think we want to make it given that given z. Sorry, that's a very crazy z. Z I K. Okay, so what is this? So let's figure out what's going on here. This conditional expectation, this expectation on the outside, it's the probability that zik equals 1 times the expectation here given zik equals 1 plus the probability that zik equals 0 times the conditional expectation given that zik equals 0. But given that zik equals 0, this is just 0. So we don't need to worry about that one at all. And we just need to think about what is the conditional expectation zik xi given that zik equals 1. And that, of course, when it's 1, that's just 1. And so we just get the conditional expectation xi given zik equals 1. Okay, so what is this? Well, let's go back up to our model. This is so we want to think about the conditional distribution of xi given zi. So back up to the model here. Oh, that's not the model. Here's the model. Given zik equals 1. So if zik equals 1, then zi equals ek. Right? The ith component is 1. So given that, that's exactly what we've defined. We've defined x to be normally distributed with mean mu xi to be normally distributed with mean mu k and covariance ck. So the expectation, the conditional expectation, is just the conditional mean. It's just the expectation of this conditional distribution. And so it's just mu k. So that's easy. That is mu k. Very nice. Very nice indeed. And so this thing becomes, like, put like, what did I put? What should I put? I'll put this, something like that. This equals sum over I. Now I said it was this expectation. We take the probability that zik equals 1 times this conditional expectation, and the probability, so maybe I'll just write probability zik equals 1 times mu k, and the probability that zik equals 1 we figured out before. Where did we? That was just this, the same thing as this, the expected value of zik, since it's a Bernoulli random variable. And so that's just alpha k. So this is just sum over I alpha k mu k. And since we're solving all of these equations simultaneously, then we can use this result from this earlier set of equations that had to hold. So we can plug in alpha k here. This equals, well, this doesn't depend on I, so this becomes n times alpha k. Sorry, this is a crazy staircase of equalities. N alpha k mu k. Alpha k equals nk over n, so the n cancels. We get nk mu k. And pulling all of that together, we get, now we have all these, this is equal to this. So if we solve for the thing we wanted, or the part of the, part of this theta vector, which was mu k, we get mu k equals this thing divided by nk. So it's 1 over nk times the sum over I rik xi. All right, so we're getting we got one more step down, step 2. And that has a very nice sort of form. This looks actually very much like the k-means algorithm, if you remember what that looked like. And this is also a very nice, pleasing sort of expression, because here we're counting, well, we're not really counting, it's, you can sort of interpret. So maybe I'll make a little aside. We got one more to do. We have number 3 to do, which is the matrix here, and that's going to give us the covariance matrix. But let me make, I'm going to have to do that in another video because I'm almost out of time here. But let me make a remark about, briefly, the interpretation of this. This zik, the probability that zik equals, or just, so probability that this equals x, that's equal to this, the expectation. I mean, the probability that zik equals 1 given xi equals this expectation. And if we think back up here to our model, think back up here, what that means. What does this conditional probability mean? That means if we're given some x, let's say, let me make it like a big, I don't know, maybe x is here. So that's x. That's x. And the probability that zik equals 1 given xi is, in some sense, so people refer to it as the responsibility. It's going to be more for this one because it's closer, well, I mean, at least in this picture, it's going to be higher for this one than this one. The probability that that zik equals that given x is higher. Okay, I have to stop. We'll continue this one more time. All right, see ya.